So we're always going to write things out something like this. The limit of x as it goes to a of a function equals L the limit. Okay? So a limit, we write it out this way. Okay? No? No. No. It's very exciting. All right? Now, one really important and wacky thing here. Something you've never had to think about in a math problem before. Let's suppose that that's our function. Okay? Why, 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 why. Okie dokie dokie. That is a function, but it's a scary function. Okay? Let's compare that function to this function. All right, now, this is like, you know that candy bar Twix where they have left Twix and right Twix? Well, we sort of have the same thing with limits. We have left and right. The only difference is that sometimes the left and right limits are actually different, where the left and right Twixes are the same, and it's a gimmick. Let's go up this line. Say I start here. I go up the line, up the line, up the line, up the line. The slope's constant, right? Up the line, up the line, up the line. I get here, and all of a sudden I'm going down the line, down the line. There wasn't any hint as I was going up here that I was going to come down here. It's kind of like driving in San Francisco. To the other hand, what happens as I'm coming up here? Well, the tangent lines are flattening out. So this curve is telling me that I'm getting to the peak and then I'm going down. And we'll talk to this a lot more in some of the later chapters. Okay? But let's go back. This guy is discontinuous. Because when I get here, I just change. This one is continuous because I can just write up, all right? There's a discontinuity there. It's the same thing as if, what happens if my graph looks like that? Well, this point is one way, and that line is a different. But right here, I have a problem. Okay? Everybody with me on this? So now, left and right. If I'm coming toward this point this way, the function's continuous till it gets here. If I'm coming at this point this way, that function's continuous until I get to there. So all through here I'm continuous, all through here I'm continuous, but there's a discontinuity in the middle of this line. Okay? Does that make sense to you? There's a discontinuity in the middle of this line. So what we do is we can calculate the limit going to the left and calculate the limit going to the right. And if we were to calculate them coming the two ways, we should know what's coming next. So all through this part, I know what's coming next, but all through this part, I know it. Okay? If this is the function I have to deal with, I really am not going to be able to do derivatives, do limits on this because I have this discontinuity in the middle. I could take this piece of it, or I could take this piece of it, but I can't do the whole function, right? I can't do the whole function. I can do the whole function. I can do the whole function. So my function needs to be continuous. An example of this, if you're saying, well, what looks like that? Absolute value looks like that. We know absolute value, right? If we say absolute value of -1 is 1, right? Absolute value of 1 is 1. So absolute value just kind of, and it's not going to be continuous. It's so exciting, isn't it? Now, he said, now, we're not too worried about the formality of the math part. Okay? We're not too worried about that. We're not too worried about that. Okay? So, again, we had this limit, and that's a m. X goes to a. F of x, that's the limit. Okay? The limit of a constant as x goes to a is a constant. Yeah? The limit of x to the n is a to the n. And you're saying, if I say if my function is x squared, that's my function, and I want to find the limit from as x goes to a of x squared, well, make that 3. The limit as x goes to 3, x approaches 3, x squared, I'm going to put 3 in for it, and I'm going to get 9. Right? Equals 9. And you're going, well, why am I doing this? It's the thinking thing. We're thinking. And it's going to get more complexical here. Okay? If I have a constant k, and I multiply that times the function, and I take the limit of that, that's k times the limit of the function. I don't include the k when I take the limit. Okay? Are we having fun here? The limit of fx plus the limit of gx, if g is two functions, I'm add them together, I get the limit of the two of them added together. Right? Limit of x with respect to a and limit to g. Okay? I add their limits together. And the multiplication of the limits is the limit of f of x times, that's a times, the limit of g of x. So if you were really bored and you were really bored in taking a calculus class for some reason because you didn't know any better, you might spend 2 whole weeks just doing limits. Yes? Yeah, I know. You're like, dudes. Okay? So, let's try some things. If I say the limit of 9 as a goes to 5, well, that's still 9. No matter what happens to a, it doesn't affect the value of 9. 9 is still 9. Yes? 9 is always 9. There's no a or x in there, right? Limit x squared as a goes to 6 is going to be 36. Limit 2x cubed as a goes to 3 is 2 times limit x cubed as a goes to 3. Yes, is 54. 3 to the third power is 27 times 2 is 54. Okay? How about limit x plus 8 times x minus 5? Well, that's going to be as x goes to 4. Okay? Well, that's going to be limit x goes to 4 x plus 8 times limit as x goes to 4 x minus 5. Okay? So I'm just going to stick the 4 in there. Yes? I'm just going to stick my 4 in there. And I'm going to get 12 times minus 1 is minus 12. Put the 4 in there. Put the 4 in there. Okay? And again, we're just doing these, but in the real world, we would do these not to do this simple little funky thing that we're doing. We do them. Why? We do them because the limit, if we do it one direction and the other direction, can tell us about continuity. Okay? And again, you're like, why do I care? Well, the answer is you need to have continuity. In grad school, those of you who aren't in grad school yet will be someday. The rest of you will be in grad school some year, whatever. You start making jokes that only you think are funny, right? That the grad students think are funny. And so we used to make jokes all the time about differentiable time. That, we kept getting interrupted. We said, look, I need differentiable time. I need to work on this. And people would understand, and they go, yeah, I know. It's not really funny, but it's life. So if this is my thing, what am I going to do? Well, I'm going to separate it out and go limit x to the 4th, x approaches 2, limit plus, that's a plus sign. Couldn't you tell? X goes to 3x. Right? Yeah? So that 16 plus 6 is 22. Yo, baby, yo. Yo, baby, yo. Yo, baby, yo. Okay. So, let's go talk briefly again about continuity. Continuity is a necessary condition to take a derivative. It's necessary. It's not sufficient, but it's necessary. Right? If the function is not continuous, we can't take a derivative. If it is continuous, it still might have a problem that prevents us from solving the problem. Okay? But it's continuous. And again, secants, right? Tangent lines. That's how we find slopes of things, secants or tangent lines. If you have a function that you can't do secants or tangent lines on, it's going to be automatically discontinuous. Okay? It's going to be discontinuous. No? Okay, fine. Don't believe me. So we need to know that there's an actual f of x. It has to be defined. Okay? Does this limit exists if limit x goes to a, f of x is f of a. Okay, so assuming we're continuous, if that equation works, then there's a limit. Okay? I can see you're excited, even though you're not here. No? All right. So a couple of things, and we're not going to spend a lot of time on this because it's just algebra and you should be practicing. But, you know, we do these things, 2x plus 3 equals, 24, and 3, yes? And 3x plus, no. 6y equals 48. And don't do that. I mean, it's a bad set of numbers, but we could also do this with this being less than, or less than or equal to. Okay? And we should understand how that works, because if I multiply both sides times -1, I have to flip the sign. Yeah, there's various operations I have to do where I flip the sign if it's an inequality. Okay? So if I multiply or divide by something positive, I keep the sign the way it is. If I multiply by a negative, I have to flip the sign. Okay? Yeah, you're like, eh? Yeah. Just try it. Okay? Just try solving these equations where there's examples in your book. It's not a big deal. But we're going to see them. We might see some of these later, and we need to, like, a lot later, like 10 chapters later. And you're probably not going to remember it anyhow if I spend a lot of time going through it. Eventually we'll do inequality constraints and Kuhn-Tucker conditions. And you might run into a greater than or less than. Okay? Okay. 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 Fine. So we know all this exciting stuff now, and we're really ready to go, do the right stuff, the real stuff.